Okay, we're going to work problem 6.11 from the end of chapter questions. Nice little problem here for a couple of reasons. It asks us, what is the change in internal energy in joules of a chemical system or system in general that releases 675 joules of heat energy to its surroundings and has 530 calories of work done on it? So whenever you're talking about calculating energy changes, internal energy changes, heat flows in general, you always have two things to consider. You have the system and then the surroundings. The system is the chemical reactor, whatever it is you're talking about. The surroundings is basically everything else. Sometimes that's called the universe as well, okay? So when you see these words, system and surroundings, you're going to start seeing that a lot in this chapter, because we're going to start talking about energy flows, okay? So don't be surprised by that. Now, if we're going to compute the change in internal energy for a system, that is delta E, is the terminology that your book gives to it. The delta, when you see the triangle, we read that as delta, the Greek symbol delta. It means change in chemistry. When you see delta anything, it's talking about change in a variable from final to initial condition. So we say delta E is the change in internal energy in this case. Now, that is always defined as being the sum of Q plus W. Q plus W. Okay, it's a plus sign in this particular equation. Sometimes in the physics literature it can be a different sign. We'll get to that here in a second, okay? But the Q stands for the variable of heat energy. It's thermal energy. Sometimes when we have a chemical reaction, that reaction can release heat to the surroundings, or maybe it absorbs heat from the surroundings, and this term accounts for that in the total internal energy. Now, the other way that internal energy can change is work. Just like the system can release heat energy or absorb heat energy, our chemical reactor system can have work done on the system, or it can have work done by the system. Okay, so that's another way that internal energy can change. And basically we have to sum these two, or add them together, to get the total change in delta E. And this is just the equation for that, okay? Now, it's a pretty easy equation. You just add numbers together. Everybody knows how to do that, all right? But the tricky part, okay, is the signs on these terms, whether they're positive or negative, because they can be either. And what the signs ultimately tell us is the directionality of the energy flow. Is it into the system or out of the system? Now in this equation, the equation that we're going to use for this chemistry class, okay, we're going to define the positive and negative sign relative to the system itself. How are things changing relative to the chemical system? Not the surroundings, the system, okay? So if heat energy is absorbed by the system, the change in Q would be positive. However, if the chemical system produces heat, which is then lost to the surroundings, my Q has a negative sign. So again, positive if heat is absorbed by the system, negative if heat is lost by the system, okay? Likewise, if work is done on the system, maybe you compress something, we'll say, okay? That's like storing internal energy into it, or adding internal energy into it, so the sign is positive. However, if the system performs work on the surroundings, or if a work is done by the system, in our lingo, it's a negative sign. This is the hardest part of using this equation, okay? Because it's the directionality of the heat flow, okay? All right, so getting into this problem then, to actually try to work it out, we want to compute internal energy change, the delta E, for this particular set of circumstances. We know that the system releases 675 joules of heat energy, that's our Q term, and it looks like 530 calories of work is done on the system, okay? So you might be super tempted to start by writing the equation, delta E is equal to Q. Well, it looks like the system that releases 675, so 675 joules is probably important, and that's heat energy, so that's my Q term, okay? And it looks like it releases heat to the surroundings, So which one do I want, positive or negative? I think I want a negative here, right? Because heat is lost to the surroundings. So notice it didn't tell you that this should be negative in the problem. You have to figure that out by yourself based on these conventions, okay? So that term looks okay. Now I got to add my work term. I got to add my W. Okay, so it looks like 530 calories might be important here, okay? And if I read carefully, because I got to assign a sign. All right, let's see. It has 530 calories of work done on it. Work is done on the system. So by our sign convention, that should be positive. Now that's true. That sign is going to be positive. But I made an error here on purpose, right? This unit of energy was in joules, capital J. This unit of energy was given in calories. Those are going to be our two most common energy units that you're going to see a lot in Chapter 6. Joules and calories. Turns out chemists use both of these. Just sort of depends on where you're from, who you studied with, which book you use, but you can use both of these, okay? And you see that in the literature. So we need to come up with a framework to convert between these units. Okay, that's very, very important. A really important conversion factor to help us do this then is that 1 calorie, 1 scientific calorie as I like to call it, is equal to 4.184 joules. Now knowing that my work involved 530 calories, I can easily convert to joules and away from calories. It's just a unit conversion. Undesirable units in the denominator, desirable on the top. And 1 calorie is equal to 4.184 joules. If I do a little bit more space, if I do the work on my calculator, that's 2,217.52 joules, okay? So in fact, what I need to do to help me answer this question is instead of reporting my work in calorie units, which don't jive with the joules, I'm adding two dissimilar things. I'm now going to add 2217.52 joules here. So I just did a unit conversion. Again, the sign is meant to be positive, okay? All right, so this is a release of the heat energy to the surroundings. This one is positive because the work was done on the system, not by the system. If the work was done by the system, that would have to be negative, okay? So to make a long story short, and to finish off the numerical aspect of this, I just have to add these numbers together. And when I do, I get 1542.52 joules as my delta E, my internal energy change. Looks like I probably want to round to 3 sig figs in that neighborhood, right? So maybe I'll just do 1540 joules. And I'm set for my delta E. That's my internal energy change, okay? That's how you work this problem. Now, one more bit of free information for you, just because it's kind of interesting. We said that there's this conversion factor between calories and joules. Now, you've probably heard of calories before. Most people have heard of that. When you think about food, right? You eat so many calories per day or whatever, right? This hamburger has 800 calories, whatever, right? It just so happens, just for your information, that food calories are actually not the same as this calorie. It's equal to 4.184 joules. We use the same name for it, but it turns out that 1 food calorie, just 1 food calorie, is actually equal to 1,000 of these scientific calories. We might call that a kcal, or a kilocalorie, okay? So it turns out that if you eat 1 food calorie, you're really consuming 1,000 of these scientific calories, okay? So our bodies go through a tremendous amount of energy each day through our food consumption. All right, but that's just a little bit of added information for you.